Hello everyone, I'm Dhiraj Madan, and in this short video we'll be learning about quantum information using the idea of CHSH game. So let's get started. Now in 2022, which is 3 years back, there were these three physicists, Aspect, Clauser and Zillinger, who won the Nobel Prize in Physics for their work in quantum information. So as you see this page from the Nobel Prize website, they won it for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Now, if these words sound a bit jargon to you, then do not worry, because essentially these ideas are very simple and we'll be explaining these in today's short video. So CHSH game is as follows, that there are two players, Alice and Bob, who are separated apart in space, so they cannot communicate with each other. But essentially there is a third party who can communicate with each of them respectively. Right? So they can communicate with the third party, but they cannot communicate with each other during the game. Now essentially, so each of these two players, they receive an input bit from the referee. So I'm going to call it X and Y. And essentially these happen to be 0 or 1 with probability half each. So essentially X can be 0 or 1 with probability half, Y can be 0 or 1 with probability half. And they need to output a corresponding bit A and B. So A can be a function of X. So Alice needs to output A based on its input X. Bob needs to output a bit B based on its input Y. But however, Alice cannot see Bob's input, so Alice can only see X, Alice cannot see Y. Similarly, Bob cannot see Alice's input, so Bob can only see Y and Bob cannot see X. Then essentially the idea is that they win the game if the AND of their inputs, X, Y, equals the XOR of their outputs, A and B. So if X, Y equals A XOR B, then they win the game. So let's see what are the conditions in which they'll win this game. So essentially, let's enumerate all four possible cases for the inputs. So if both the inputs are 0, X and Y are both 0, then X and Y is going to be 0. The winning condition is that A XOR B must be 0, which means that A and B must be equal. If A and B are unequal, if the outputs are unequal, then they lose the game. Similarly, in the cases where X is 0, Y is 1, again X, Y is 0, and essentially again the same idea holds, that essentially they are going to win the game only if A XOR B happens to be 0. In the third case, when X is 1 and Y is 0, so essentially X and Y is going to be 0, here they win the game if A XOR B is again 0. In the fourth and the final case, essentially they win the game if XY happens to be 1. If XY and if both of them are 1, then XY happens to be 1. They win the game if A XOR B also equals 1, which means that both the outputs are unequal. So what do you think could be a simple strategy to win this game, and what could be the probability of winning in that strategy? So the idea is that if you always output 0, then essentially you win in 3 out of these 4 rows, and you win the game with probability 3 on 4, right? Now the thing is that, can we do better? Well, the answer is not, because if you need to do better, then you'll have to win in all 4 possible cases, and it turns out that it is impossible to win in all 4 possible cases. Even if you share randomness, it will not be possible. So the idea is that, now how does it relate to quantum? Well, the idea is that if you use the ideas from quantum information, which we are now going to describe, we can win this game with probability more than 3/4, and that winning probability is cos square pi by 8, which is 0.85, right? So that's going to come next. So before, in order to understand those ideas, let's first go back to basics and understand, what exactly does classical physics tell us about this world. So if you know Newtonian mechanics, then you would know that, everything is deterministic, right? If you know the current positions and velocities of each particle in the universe, you can essentially use the dynamical laws or Newton's second law to determine the positions and velocities at every point in the future. So this world is going to be completely deterministic, and of course you can get the complete information about the world. This is the main crux of, or the main idea behind quantum mechanics. And essentially this was essentially the way the things worked, and people accepted these things until the turn of the 20th century, right? So this ideas of determinism, right? So these are also known as Laplacian determinism, but essentially you can trace them back to Newtonian mechanics. Now, at the turn of the 20th century, there were a few physicists such as Max Planck and Schrödinger and later Heisenberg, who essentially developed a new theory. And the reason was that there were some of these experiments which, as I said, conducted by Max Planck and even Einstein, right? The photoelectric effect by Einstein or black body radiation by Planck, which could not be explained using the ideas of classical physics. And essentially we needed a new mechanics, which was then developed subsequently by Schrödinger, Heisenberg, and later even Feynman towards the second half of the 20th century, which essentially tried to reconcile these sort of new experiments which had come up. And essentially they needed a new language, a new sort of mathematics, a new sort of physics to explain this, and that's how quantum mechanics was born. And essentially the idea is that this is going to be probabilistic. Here essentially you cannot have complete information about the world, so the state is essentially hidden until measurement, and the state variables are incompatible with each other. For example, you cannot know the position and velocity of a particular point simultaneously. Any particle, you cannot know its position and velocity simultaneously. So what implications does it have for computation? Well, let's see. So in classical computing, we are used to the idea of classical bits. So a bit can be either 0 or 1. And essentially the way the computation proceeds is via these Boolean gates, which are AND or not, right? And you can also have a universal gate, for example, NAND. Now, essentially all our computers, all our devices are based on these ideas of these bits which come from the classical determinism. But is it the ultimate thing? So that was what physicists towards the end of the 20th century were questioning. So Feynman had asked that can we simulate quantum mechanics using classical computer efficiently? Well, the answer is no, because essentially if you need to simulate quantum mechanics using classical device, then you will need an exponential number of resources. So what can we do? And what Richard Feynman suggested was that we can essentially have our computing devices based on these laws of quantum mechanics. And that's how the idea of quantum computing was born. So at the fundamental level, these quantum computers, they proceed on the idea of qubit, right? Or a quantum bit. So just like a bit can take a value 0 or a 1, so qubit can take a particular value which we are going to denote as ket 0 or ket 1. But it can do something more. It can also lie in a superposition of these states, alpha ket 0 plus beta ket 1, right? Which is superposition of ket 0 and ket 1. Here essentially alpha and beta are complex numbers such that the norm of this vector alpha beta is 1, or mod alpha square plus mod beta square is going to be 1. Now, what does this all mean, these complex numbers, this superposition? Well, essentially you can consider these ket 0 and ket 1 to be these two-dimensional complex vectors. So ket 0 can be represented as a vector 1 0 and ket 1 can be represented as a vector 0 1. The general state ket psi can now be written as alpha beta. Now a superposed state ket psi, if it is alpha ket 0 plus beta ket 1, what do these alpha and beta even mean? The idea is that if you make a measurement, essentially you will get one of these two classical bits, either 0 or 1. And what these alpha and beta, what they would suggest is that the mod alpha square and mod beta square, they are essentially the probabilities of getting a 0 or a 1. Now essentially we can of course measure in the standard basis. Can we do something more? Well, we can also measure in the rotated basis. So essentially if you express ket psi in terms of rotated basis, let's say v and v perp, then you can write ket psi as alpha prime v plus beta prime v perp. And essentially now if you can make a measurement in this v perp basis, so you'll get v which corresponds to the output bit 0, which happens with probability mod alpha square, or v perp which corresponds to the output bit 1, which will happen with probability mod beta square. So how does it even lead to an advantage, right? So if you go from a single qubit to 2 qubit, now you can be in a superposition of all 4 classical states, get 0, 0, 0, 1, 1, 0 and 1, 1. And if you go to n qubits, you'll get a superposition of all 2 to the power n classical states. One example here is the well-known EPR state, which is like 1 by root 2 0 0 plus 1 by root 2 1 1, which is a 2 qubit state. And essentially, as we go towards these ideas of these n qubits, we can get an exponential advantage over the classical computing. Now, if you have this sort of this EPR state, and if you make a measurement, you'll get 0 with probability, both 0 with probability half and both 1 with probability half. And this will happen even if, these qubits are separated light years apart. And essentially this leads to, somewhat paradoxical situations. And essentially this EPR, these initials, they stand for Einstein, Podolsky, Rosen, who were, who weren't convinced by these ideas of quantum mechanics, and they constructed these states to give an counter example to sort of quantum mechanics. And Einstein had remarkably, he had said that at any rate, I'm convinced that, he or God does not play dice, or, the universe is not random. However, there are some strategies which, if you use these ideas of these quantum entanglement, you can design some strategies which will allow you to win the game with probability more than 3/4. And essentially that exactly is cos square pi by 8, which is roughly 0.85. And it turns out that, this turned out to be a crucial test for quantumness, that, if you can win this thing, then essentially you can show that quantum computer is strictly more powerful than classical one. And these ideas, they have been verified experimentally using the notions of Bell tests. This essentially confirms that quantum mechanics, it cannot be modeled via these local hidden variables. So those of you who are interested in more such games and their sort of probability analysis, there is a full sort of a YouTube course. I can provide a link to the same. So I'll ask the organizers to share that link with you. And to conclude with, I would say that once these tests were verified, which happened in 1960s, right? So some of the physicists whom I mentioned in the Nobel Prize, who were the Nobel Prize winners, they were part of the people who were able to verify those Bell tests. So essentially, it turned out that once those tests were verified, then it turns out that that one has to reconcile with the fact that the universe is essentially probabilistic and random, and it cannot be modeled via these local hidden variables. So Einstein, towards the end of his life, he pursued this idea of local hidden variables very vigorously, but he failed, and later the experiments showed that we'll have to accept quantum mechanics. We cannot use these hidden variables to reconcile these ideas in the new physics. And essentially what it also shows is that God, or the God actually, or the universe essentially does play dice. The nature is essentially random. So that's the conclusion I would leave you with, and thanks. Hope you enjoy the rest of the talks. Goodbye.